Scientists just fixed one of the biggest problems standing between us and real, scalable quantum computers. They found a way to make a magnetic wave carry quantum information 100 times longer than before, and it might let us build a working quantum computer the size of a coin. To understand why this matters, you first need to know what a magnon actually is. Inside a magnetic material, countless tiny atomic spins are all lined up in the same direction, like a field of compass needles. A magnon is a ripple that travels through that field. One spin tilts, nudges its neighbor to tilt too, and that disturbance propagates outward as a wave, without any of the atoms themselves actually moving. Physicists treat this wave as its own quantum particle called a magnon, and the entire field of studying it is called magnonics. Magnons have been on physicists' radar for years as a possible way to move quantum information around inside a computer chip, because unlike an electrical current, a spin wave can carry information with very little energy loss. If you could reliably store and transport quantum information as magnons, you'd have a fast, low-loss messenger for connecting different parts of a quantum computer together. But there's always been a fatal flaw. Magnons are notoriously short-lived. In most materials, a magnon's quantum state collapses or decoheres in a matter of nanoseconds, far too quickly to be useful for storing or transporting quantum information. A messenger that forgets the message before it arrives isn't a messenger at all. For years, this made magnons feel more like a theoretical curiosity than a practical building block. Researchers have tried other quantum messengers too. Photons, particles of light, carry quantum information well over long distances, but they're difficult to confine and route inside a compact chip. Phonons, vibrations of the atomic lattice itself, have also been explored, but they come with their own coherence limits. Magnons had a real advantage in size and integration with existing magnetic materials, but their short lifetime kept ruling them out as a serious contender, no matter how promising the theory looked on paper. None of this came out of nowhere. Spin waves were first described mathematically all the way back in the 1930s by physicist Felix Bloch as a way to explain how a material's magnetization weakens as it warms up from absolute zero. For decades afterward, magnons stayed mostly a subject for theorists and specialists in condensed matter physics, interesting on paper but with no clear path to a real application. It's only in the last 15 or so years, as the broader field of spintronics matured, that magnons started being seriously considered as a working part of quantum technology rather than just a textbook curiosity. That changed in May of 2026. A research team reported that they had extended a magnon's coherence lifetime to 18 microseconds. That might sound tiny, but compared to the nanosecond lifetimes researchers were used to, it's roughly a 100-fold improvement, long enough for the first time to seriously function as a quantum memory rather than a fleeting disturbance. The breakthrough came from a genuinely international collaboration led by the University of Vienna, working alongside the University of Colorado Springs, and additional research groups in Germany and Ukraine. It's the kind of result that took multiple specialized labs, each contributing different expertise, to actually pull off. So how did they do it? The team worked with spheres of yttrium iron garnet, often shortened to YIG, a material long prized in magnonics, for how cleanly it supports spin waves. Instead of exciting the more commonly studied long wavelength magnons, they specifically excited short wavelength magnons, which turned out to be dramatically more resistant to losing their quantum state. Combined with extremely high purity material, this specific choice is what unlocked the dramatic lifetime jump. None of this works at room temperature. The YIG spheres had to be cooled to 30 millikelvin, a fraction of a degree above absolute zero, and colder than the vacuum of deep space. At that temperature, random thermal jostling that would otherwise instantly scramble a magnon's quantum state is almost entirely suppressed, giving the fragile spin wave a real chance to survive long enough to matter. Here's the part that genuinely surprised the researchers. They found no fundamental law of physics that caps how long a magnon can survive. The limiting factor was always materials science, impurities and defects in the crystal scattering the spin wave and destroying its coherence. That means this isn't a hard ceiling. As material purity keeps improving, magnon lifetimes could keep extending well beyond what's been demonstrated so far. It's worth sitting with why that materials science framing matters so much. In a crystal like yttrium iron garnet, even a handful of misplaced atoms or microscopic defects act like tiny obstacles for a passing spin wave, scattering it and bleeding away its quantum information a little at a time. Grow a purer crystal with fewer of those defects, and the spin wave simply has less to collide with. That's a fundamentally different kind of problem than something like the speed of light, which no amount of engineering can ever get around. Purity is a target you can keep chasing, refinement by refinement, rather than a wall you eventually hit. This unlocks something quantum computing has been missing: a quantum bus. In classical computers, a bus is simply a shared pathway that lets different components talk to each other. Quantum computers have never had a reliable equivalent, a way to link many qubits together on a single chip without losing the fragile quantum information along the way. A long-lived magnon can now act as exactly that kind of connector. That solves one of the field's most stubborn scaling problems. Today's quantum computers are largely bottlenecked not by how many qubits you can build, but by how many you can reliably connect and control together. A magnon-based quantum bus could let hundreds of qubits share information along a common path, instead of requiring a tangle of separate, error-prone connections between every single pair. Because magnon-based components can be integrated directly onto compact magnetic chips, researchers say this approach could eventually shrink a functional quantum computer down to roughly the size of a 1-cent coin. Today's quantum computers still fill entire rooms with cooling equipment and control electronics. This is a genuine path toward collapsing that footprint dramatically. Beyond quantum computing, long-lived magnons are also being explored for ultra-sensitive magnetic sensing and for low-power on-chip communication, since spin waves can carry signals with far less energy loss than ordinary electrical current. None of these applications are finished products yet, but they're active directions the same underlying discovery opens up. For years, magnons were treated as too fragile to take seriously as a quantum computing component. This result flips that assumption. It shows that the ceiling researchers assumed was fundamental. Physics was actually just a materials engineering problem waiting to be solved, and that a missing piece of the quantum computing puzzle may have been sitting inside ordinary magnetic materials the entire time. None of this means a coin-sized quantum computer is showing up next year. 18 microseconds is a huge improvement over nanoseconds, but it's still a lab result, achieved under extreme cryogenic conditions with a single carefully prepared crystal, not yet a component sitting inside a working quantum computer. Turning a promising physics result into deployable hardware historically takes years of further engineering. What makes this genuinely significant isn't that the problem is solved. It's that researchers now know it's solvable at all. A magnetic ripple that can now hold on to quantum information 100 times longer than before, and possibly shrink an entire quantum computer down to the size of a coin. Does this change how you think about where the next quantum computing breakthrough will come from? Let me know in the comments. New discoveries unlocked daily. Subscribe so you never miss one.